Hello guys, good morning, and how are you guys doing this morning? So my name is Olagbimi Emmanuel Odonayo. As you all know, then people used to call me Prof. So that is my student all over the country and even abroad, because we have students abroad presently. Now this morning before we start, we discovered that some of our students, they are finding it difficult to relate or to solve chemistry. So sorry, I'm coming. My microphone just dropped. Okay, thank you. Welcome back. So some of my students, they're having it difficult to understand chemistry and some concepts under chemistry. So we have taken it upon ourselves to ensure that we make chemistry so easy for every individual to understand. And this time around, we are going to be talking on a topic. The topic is entropy. Entropy and entropy change. So like I said before, it is not easy, because this morning we are just starting, and it is not going to be perfect the way you guys are thinking, because when you just start a program, it is not going to be perfect, but later, by God's grace, it will. The reason is, like this morning, we just have to use our phone. So I was trying to use the front camera so that even me myself, I can see what I am teaching. But I discovered when I wrote on the board, I was only getting the mirror image of what I was writing. So I had no option than to tell my wife not to go for work. I pleaded with her, so my wife loves you, so she abandoned her job this morning just to ensure this online class hold. So she's standing behind my camera presently, so you guys need to give her a very good kudos, or maybe bosa. So then, since we are using phone, we are supposed to be using laptop. There are many things that may not be working well. Number one, sometimes the network, we are in Nigeria, is going to be giving us a problem. So sometimes we just accept the way it is this morning. So by God's grace, this morning, let's go back to the real work. This morning we are going to be saying a topic: entropy and entropy change. Entropy and entropy change. Now, the last time we met physically, we discussed entropy and entropy change, and we were told that entropy is the total amount of internal energy present in a body or a substance, the total amount of internal energy. And we discussed the entropy change, so we're able to see the exothermic and endothermic reaction, the reaction that liberates it to the surrounding from the reacting system. That one is exothermic reaction. And the one that absorbs it from the surrounding into the system, that is an endothermic reaction. And we have given different examples of endothermic and exothermic system. So one of the examples of exothermic system, like for example, even at home, do you remember you cook? If you don't cook, your parents cook. They cook. And when they cook, the heat is being liberated into the surrounding. And in chemistry, instead of saying cooking, we actually used to say, we say combustion. We are burning. Combustion takes place in the presence of oxygen. So it's all evaporation reaction, neutralization reaction. And when you go to endothermic reaction, we have decomposition reaction. So we are not going to be talking about that one now. I only refresh your memory on that. Now this morning, we are going to talk about entropy and entropy change. What do we mean by entropy? Before we continue, Entropy has a symbol. The symbol of entropy is S. Why, when I talk about entropy change, that one has a symbol of change X, that is entropy change. That is the symbol we normally use in science to represent our change, this symbol. Now, as we continue, we equally see, we are going to see our objectives. Look at the objective we have at the end of the class. We should be able to achieve this change. We are going to be defining entropy, and we are going to define entropy change. Then we are going to give examples of entropy system. Those one around us, those one far away from us, those of entropy system, those physical and chemicals. Then we are going to talk about the process with positive entropy change. So we are going to talk about the process with positive entropy change. Then lastly, we'll be talking about the calculations. We are going to solve little problems on entropy change. At the end of this class, I believe there is no question you are going to see in your UTME if you are writing UTME, in your WAEC if you are writing WAEC, in your NECO or your NAPTEP or any external exam that you will not be able to smash. That is the logo. You smash it. So you are going to smash it. So as we continue, we are going to talk about the first objective. Let's see the definition of entropy. Then we are going to give an example. Then we go to entropy change. What is entropy? Entropy can be defined as the degree of randomness or disorderliness of the system. I repeat, it can be defined, entropy can be defined as the degree of randomness or disorderliness of a system. Now let me give you an example. We have three states of matter. We have the solid. I believe, please, if there is any problem with what we are doing, you can go to comment section and comment. You understand? So that if the audio is not loud enough, you are not hearing me enough, then, or if the network here is somehow skipping or whatever, you can.
It's slow. Slow.
It's slow.
Yes.
The network.
It's slow connection.
Okay, if you have a slow connection, so you can equally comment. So we are going to know. Thank you. Now, let's come back to the chemistry now. I said we have three states of matter. The first one is solid. We have the liquid, and we have the gas. Now, you know, each of these states has particles, and you are told in your junior class that the particles of solids are closely packed together, in which there is no or little distance between the particles. They are very closely packed together. Now let's come to liquid. In liquid, the particles, they have little spaces between them. So the particles can easily, move. So the particle can easily move. But when you go to gas, you have enough space between gas particles. Enough space between gas particles. Look at it. When you come to liquid, I can put all this, meaning the particle here can easily come to the particle. A very good example is when you have a water and you put a particle inside water. Then what do you experience? You can put your hand inside it and shake the particle. That is the reason why sometimes we used to say a liquid can translate. The particle can move from one point to another when you disturb it. Then when you go to a gas has, the force of cohesion in gas is very negligible. Very negligible. So the force is too weak. The particles can easily, they are far from each other. So no wonder if you open it, or else, even if you compress the gas to form a liquid, if you open it, what happens? It disappears. Now, the particles in solid, they are in orderly manner. The particles are well arranged. So, when you look at this particle, the entropy here is very low, because if you go back to the definition, I said it is the degree of randomness or disorderliness of a system or of a substance. Now, look at it. There is no random movement. There is no disorderliness. Everything is well arranged. They are in order. The particles are in order because they are not moving. So, they are completely in order. They are not moving. But when you go to liquid, the particle can move from one place to another, at least from one point to another. They are free to move a little bit. So liquid have higher entropy than solid because there is a disorder, a little bit disorder if the particle moves or if the particles move. Then when you get to gas, you discover in gas the particle is far away or they are far away from each other. So the entropy in gas is very, very high. So if I'm going to put it together, I will say solid is less than liquid, while liquid is less than gas. This is the order of the increasing entropy. So gas has the higher or the highest entropy, followed by liquid, and lastly by solid. Now we are going to see the unit of entropy. The other time I gave you the unit of entropy, and I told you it is measured in kilojoule per mole. But entropy is measured in joule per mole per Kelvin. So it is measured in joule per mole per Kelvin. Or if you like, you can say joule. If you like, you can say joule per Kelvin per mole. So whichever way, you are still correct. Without wasting time, we are going to see the definition of entropy change. Entropy change. I'm going to clean this. If you have any question you need to ask me, you can easily go to my WhatsApp and send me any question. You understand?
Sure.
Whether voice record or whether or anything, or you can even put it in the comment section. So we are going to check all your comments. But the best place where you can give me your question is on WhatsApp. And in case you don't have my WhatsApp number, I'm still going to give you my WhatsApp number, which is 070-62-344-857. So that is it on the board. So let's see entropy change. Entropy change. How do we are going to give the theoretical definition of entropy change as well as the mathematical definition or mathematical expression of entropy change. So entropy change can be defined as the state of orderliness or disorderliness that accompany a physical or chemical process. The state of orderliness or disorderliness that accompanies a physical or chemical process. Then mathematically we are going to see the definition of entropy change, which is the sum of the products minus the sum of the reactant. Look at it. Entropy change of a reaction or system. You know, I told you the definition of system. It is the substance you are working on. That is system. If the entropy change of a reaction or system is equal to sum of entropy, you can say if I put this file, this is standard entropy, sum of standard entropy of products minus sum of standard entropy of reactants.
So come again.
So I am going to say this, the network bar.
No, come again. Someone said please come again.
Okay, someone saying I should come again. Which one is it? The definition? Okay, let me go back to the mathematical expression, the definition, or let me start with the theoretical definition of entropy. Please, I want you to talk at the comment section. Is my voice audible enough? I want to know from the comment section. Is my voice audible enough? If you're having any challenge with my hearing, with hearing my voice, that means you should check your network so you can actually leave that area and go to where you have a better network. So I'm going to define entropy change again. Maybe I'm too fast. Please, I'm going to be taking it slightly now. Entropy change can be defined as the state of orderliness. Thank you. Can be defined as the change of orderliness or disorderliness that accompany a physical or a chemical change or process. Now, you should be asking me a question that when I was defining entropy, I said it is the degree of disorderliness of a system or of a substance. But this time around, I'm talking about entropy change as what? A state that is, that talks about disorderliness and orderliness together. Now, for instance, let's say you have A reacting with B to give you C plus D. You know, initially, before the reaction proceeds, the reactant A is reacting with B. The particles initially they have low entropy, meaning the particles are not moving because collision has not started taking place. Now, by the time you now add A with B, collision will now start. You remember your collision theory. Before a reaction can proceed, there must be an effective collision. The particles must collide with each other in order to form the product. So A will have a perfect collision with B. The particles now, the ions, they will now, you know, when I talk about particle, I can talk about atom, molecule, or ion. But in this form, the particles, let's say in form of ions, they are going to be colliding with each other. You understand? Remember, before the collision, the particles were having a low entropy, meaning there is little or no movement among the particles. But now, when the reaction now starts, when you add the two together, let's say you have salt and water. When you now add them together, the salt is going to dissolve in the water to form ions. And those ions will now continue to collide with one another for a product to be obtained. Meaning, initially there was orderliness, and finally there is what? Disorderliness. That is why we say entropy change. There is a change from orderliness to what? Disorderliness. So it is a state of orderliness or disorderliness that accompanies a physical or chemical processes. Now, like I said the other time, we want to see the calculation, the mathematical expression of entropy change. So this is entropy change of a reaction. That reaction I wrote the other time is equal to, this symbol stands for sum. Sum of entropy standard. This is standard. When you say something like this, we call it standard in chemistry. Standard entropy of the product minus sum of standard entropy of reactant. Why not entropy change?
Okay.
Thank you. I'm very sorry. So my wife just told me the network here is somehow bad. So thank you very much. Say a very good thank you to my beautiful wife. Thank you. Now, the entropy change. Why not saying it is entropy of product minus entropy of reactant? Why sum? It is not all reactants that is one compound. Not all products that is one. You understand? Now, we have sometimes the reactant may be more than one. We have A plus B to give you C plus D. So during the calculation, we are going to talk about the entropy of, that's the reason why I call it sum of, you need to add the entropy of this and this together minus entropy of this and this together. Please, at the comment section, let me just know whether you are getting what I am saying, or you want me to repeat or to recap all I have said. Now, we are still going to see this calculation, but before we come back to the calculation, let me just give you an instance. Let's assume we have a compound like Ca calcium carbonate, CaCO3 solid, when you heat it, CaCO3 solid, when you heat this, you have calcium oxide solid plus carbon 4 oxide gas. Now let's assume we have this reaction. Now you want to write the expression for an entropy change. Now, how will it go? We have, it's going to be this. Remember, this side is the product. Why this is the reactant. If you check it very well from the board, you will see that we have two products. And when you check it, we have only one reactant. Now, if I want to write the system, I will say my entropy change for my reaction.
Someone said I don't understand.
Okay. Okay, someone said it's not getting it. So I will come back to this equation. No, I only gave an example. Listen, I only gave an example. We want to work on this example. We want to write a formula for this example using this entropy mathematical expression. So let me start again. This equation does not concern you for now. I only gave the equation as an example. But you know, you must have done chemistry before, or you are doing chemistry now. This is the product, and this side is the reactant. All I want you to identify is to know the product side. Your right hand side is the product side, while our left hand side is the reactant side. Now, at the product side, all we want to do is product minus reactant. That is it. Just from our equation, from our expression, from our, what's it called, mathematical expression, our formula, which says entropy change is equal to, entropy change is equal to entropy of product, sum of it, minus entropy of reactant. I will try as much as possible to take it calmly. Now, let's assume we have this equation, and we want to write the entropy expression for this equation. Now, we have entropy change of the reaction. This is the reaction. Take it. Some people used to mix it up. This is the reactant. This is the product. Or we call them products because we have more than one. Then this is the entire thing is a reaction. So this is reactant, product, but this is a reaction. Now, my entropy change of reaction now is equal to, you see, sum of entropy of products. How many products do we have? Of course, we have two. This is the first product. I'm going to write entropy of this product, calcium oxide solid. Standard entropy of calcium oxide solid plus, that's the reason why I call it sum of, if you have done that in mathematics before, I think in statistics. Standard entropy of calcium oxide solid plus standard entropy of carbon 4 oxide gas. That is my product. And for you to have a perfect mathematics or calculation, put this one inside brackets. This is my product minus then the reactant. So I will now call my reactant standard entropy of calcium carbonate, CaCO3 solid. Did you get that now? So that is the expression. As easy as that. The only thing you need to add now is just the numbers, the figures, the data you are given. You will just put it and get your answer. It is going to be as easy as normal mathematics. When you give primary student 1 plus 1, they will tell you it is equal to 2. So I believe we are getting it. So if you did not get it, you can go back and watch the video again and again. You are going to get it better. Now, the next thing we are going to see, I want you to understand that there is an external factor that is majorly affecting entropy system, and that factor is temperature. We are going to come back to this place to see when we get to this calculation. By now, we are done with definition of entropy and entropy change. We have given an example of entropy system. When I told you, I gave you an example of solid, liquid, and gas. Solid, liquid, and gas. So that's an example. You understand? So, or let me simply say, when you go back to, when you have a soup, let me take you back home. When you have a soup in the morning that you have not warmed, you discover that the soup is going to be orderly arranged. But the moment you take the soup and put it on your gas or your stove or whatever thing you are using, you will discover that the soup is going to gain an energy. Immediately you increase the temperature of the system. So, by the time you increase the temperature of the system, there is going to be a disorder among the particles. You will now discover that the particles are in a disorder, in a disorderly manner. So that is what we are saying. That means when you increase the temperature, you are actually increasing the entropy of that system. Thank you. Now, that is temperature. So the external factor is temperature. And I have told you, when you increase the temperature, you are equally increasing the entropy of the system. Now we want to see some processes with positive entropy. We have entropy. Entropy change can either be positive or negative. And I'm going to tell you, when do we have a positive entropy and when do you have a negative entropy? And it can equally be at equilibrium. I mean when entropy is equal to 0.
Comment. Prof, in the formula you wrote, sum of entropy of reactant, but as you now substituting, you wrote entropy of reactant. Sorry, just say.
Please read it again. Okay, this one says, Prof, in the formula you wrote, sum of entropy of reactant, but as you are now substituting, you wrote entropy of reactants. If I could get that question from what I wrote the other time, I wrote this. B is the reaction. CaCO3 solid to give. Please, some of these questions you just have to ask me on WhatsApp because of our time. We need to work with time. Then we have CaO solid plus CO2 gas. Now from here, this is the product, this is the reactant. Everything is a reaction. So entropy change of reaction. This is a reaction. Reaction means for everything, for the system, the entire system, is equal to entropy of products, sum of entropy of products minus sum of entropy of reactants. This is my product side. How many products do we have? We have 2 products. So from here now, I will say my entropy of reaction, entropy change of reaction now is equal to entropy of product. You will write this of product. This is the first product, CaO, is a solid. That's my product, plus entropy of the second product, CO2 gas. That's the reason why I call it sum of entropy of product. Then I put it like this, minus the reactant, not reaction, the reactant, entropy of CaCO3 solid. This is the reactant. This one they are products, while this one is a reactant. So, and I told you, products minus reactant. So, sum of entropy of product. Assuming we have 2 here, I'm going to put 2 here. There is another thing I need to say here. Let's assume, we are not assuming, it is not there. Let's assume this place is when you are balancing it, because the equation is naturally balanced. If you are balancing your equation, let's say this one has 2, and this one has 3. Or let me put this one here. This one has 2, and this one has 3. You know, when you write the sum of entropy of this product, you must multiply it by these 2. You will say times 2. Are you getting it? Then this one, let's assume it has 3. You will say this one times 3. You are going to see it when we start the calculation. So maybe by the time we start the calculation, you are going to understand better. Sorry, I'm not going to be going back now. So until we get to the calculation section. Now, I told you entropy can either be positive or negative or 0 entropy change. Now, if your entropy of products, please, I want you to calm down now and listen to me. P stands for product, R stands for reactant. If your entropy of product, the value after your calculation, you understand, or physically, you know, when I was defining it the other time, the entropy change, I talked about accompanying physical and chemical change. Physically, you are able to see that this product is more than the reactant. If your entropy of product is greater than entropy of reactant, if entropy of product is greater than entropy of reactant, then your entropy change will be positive. I think we can get it. Is it loud enough? Is it clear enough?
Yes, sir.
Are they seeing it on the screen?
Yes.
Are you seeing it very well on the screen?
Yes.
Good. Then, if your entropy of products is less than entropy of reactant, then your entropy change is going to be negative. So, if this entropy of product is greater than entropy of reactant, your entropy change is going to be positive. If your entropy of product is less than entropy of reactant, then your entropy change is going to be negative. Now, if your entropy of products is equal to the entropy of reactant, then your entropy change will be equal to what? 0. That system is going to be at equilibrium. So it's going to be 0. Now, let's see examples of the system that have positive entropy. When I say positive entropy, it means the reverse of that system is going to be what? It's going to be negative. When I talk about the positive entropy, the reverse of that positive entropy is going to be negative, meaning the opposite of plus is minus. Now, I am going to write some examples. Then from the example, I will explain better. Let's consider the state. Okay, let me see the following example. Processes with... Okay, so I was told the network just, what is it called? Stop the process. No, this is a process. So, processes... I said processes with positive entropy changes. We are going to see number 3 now. You see we are progressing. Now let's see processes with positive entropy changes. Number 1, melting process. Melting process. Now, what is melting? Melting is just a process through which solid changes to what? To solid changes to liquid. When a solid melts, it will change to liquid. If you remember the example I gave you the other time, I told you, I said when a solid changes, it's made into liquid, and entropy in solid is low, very, very low. Very, very close to 0. Then the entropy in liquid is higher than the entropy in what's called in solid. And the degree of disorderliness between solid and liquid, you can understand, between solid and liquid, the degree of disorderliness increases. It is not decreasing because solid is changing to liquid. Look at it, melting process. When a solid melts and change to liquid, the entropy is going to be what? Is going to be positive. Let me show it with an equation. When you have H2O, you know, when you put your water inside freezer, you are going to get a solid water, H2O solid. And H2O solid just changes to H2O liquid. If I should ask you a question that between solid from the reactant to liquid, which one, when this side has more disorderliness, the product side, you remember it's product minus reactant, when the product side has higher degree of disorderliness than the reactant, it's going to be positive. So when your solid changes to liquid, it melts and changes to liquid, then the entropy system or entropy change is going to be positive. Then the reverse reaction, when a liquid is what? Cool and changes to, that is freezing process, and changes to what's it called, solid, what happened is going to be from randomness movements of the particles, or from what is it called, disorderliness movement of the particle, is going to be arranging together to form a solid, meaning the entropy will be reducing until it gets to zero. So, but in this one, I said the melting process is a process through which solid melts and change to liquid. Then, in that case, my entropy change is positive. You may be asked that kind of question in your exam, that what is the value of the entropy system if solid changes to liquid? Is going to be what? Positive. Then if liquid changes back, that's a reversed equation. If liquid changes back to solid, it's going to be negative. So number 2 is boiling process. Boiling process. You know what happened in boiling? When you apply heat to a liquid and it changes from liquid to vapor or to gas. For instance, when you have H2O liquid and you heat it, this one as well you heat, this heating now, you heat it and it gives you H2O gas. That's a vapor. Then between this one is liquid. The entropy here is low. While this one is a gas, the entropy here is more than this one. Why? The particles here, they move around. Then the particles here, actually they move, but not as the way they move in a vapor. So the entropy change here is positive as well. It's positive. Then if you reverse it, it's going to give you negative. Then another one is reaction in which mole of gaseous products are more than the mole of gaseous reactant. Reaction, I don't know, maybe you are saying the down part. The reaction in which the moles of gaseous products is more than gaseous reactant. The reactions in which the moles of gaseous products is more than the gaseous reactant. Now, look at what I said. I put the word gaseous and gaseous. At the reactant side, you see gas, and the product side, there is also a gas. Now, how do you determine whether the entropy is increasing or the entropy is decreasing? A very good example here is, I'm going to see what's it called? Well, let's have ammonia. When you have your NH3 gas giving you nitrogen gas plus hydrogen gas, then we need to balance this. This is 2, then this is 2. Okay, sorry, this is 3. Thank you. So this is NH3 to give you NH2 and 3H2 gas. You remember this reaction is what is it called? Is is reversible. It's reversible. So in this case, how do you know the total entropy of the system? Which one is it increasing or the entropy? How do you determine the entropy change? Is it increasing or decreasing? You calculate the number of moles. This is the reactant, while these are the product. At the reactant side, you have just 2 moles. How do you get mole? The number at the side here is the number of moles. You have just 2 moles. Then at the product side, there is one here. You have 1 mole plus we have another 3 mole at the product side. The product making 4 moles in total. So how do you now know? How do you now depict if the entropy change here is positive or negative? Look at it. The one with iron. Let's go back to what I wrote. The reaction in which the moles of gaseous product. This is the gaseous product. You only look at it. And nitrogen is a gas. Then check another gas here, which is hydrogen. And the reactant as well is also a gas. Thank God. Everything is a gas. So I can work with everything. You check the gases. The number of mole of these gases here is 1 and 3. So 3 plus 1 will give you 4 moles. The number of mole of the gaseous reactant is just 2 mole. Which one is more? The product. So meaning that the entropy of the product is greater than the entropy of the reactant. If you go back to what I said before, entropy of products is greater than entropy of reactant. So, and I told you when you have something like this, the entropy change is going to be positive. It's going to be positive. So here now, the entropy change is equal to positive. How come? What if I reverse the equation and I put my, I told you the other time I only put a forward reaction. If I put a reversible reaction, if I reverse the equation now, this one is going to be my reactant, this one is going to be my product. Then the entropy change is going to be opposite of what we have here. Then number 4, I want to clean this one now. Then we go to number 4, reactions in which.
Sir, they can't see the other side.
Okay, you are not seeing the other side of the board.
Um,
Can I continue? Can you see it now? Please, I want you to type at the comment section whatever you're experiencing.
No, I can see.
Good. Now, can I continue? Now, let's see another example. We have seen melting process. We have seen boiling process. We have seen the reactions in which the mole of gaseous product is more than the mole of gaseous reactant. Now, we want to see let's see dissolution process. Number 4, dissolution process. Number 4, we have dissolution process. You know what that means? Or processes. You know what that means? When you dissolve, let's say you carry sodium chloride. Please, can you see my board from down? Okay, I think we can all see the board. When you take, let's say you have sodium chloride, that's your common salt, you add it to water, H2O liquid. From this place, because you add it to water, you are going to have, oh, sorry, they just took the light now. I am going to on my inverter. Please, can you please on the inverter for me? Sorry, please, can you give me 1 minute? I am so sorry. They took the light. Is it clear enough now? Are we together now? Sorry, you see, behind every successful man there must be a woman. My wife just went outside to receive a call and they took the light. So I have to do all the work. So, but she's back now. Thank you very much. So, is it clear again? Please let me check.
Yes, it is. I'm online.
Now, the solution processes. We have sodium chloride. When you add it to water, the normal sodium chloride, don't think it's something big at all. When you take your salt, sodium chloride, you put it into water, you are going to have Na plus aqueous plus Cl minus aqueous. So, you can see this place is solid, this one is liquid, and in aqueous solution, there are particles that are colliding with each other. Those particles are in ions. They are in ionic forms. So they are colliding with it, with one another. So the entropy of this product is greater than the entropy of the reactant. Then my entropy change is equal to positive. So my entropy change is equal to positive. So I'm going to clean this side so that I can write the other positive processes for entropy change. So another process is expansion of gases. That's I think it's number 5. Number 5, expansion of gases. When a gas expands, there is a decrease in pressure and increase in volume. A gas, just for instance, you have a balloon. Maybe you have never asked yourself a question that when you go to an occasion, the balloon, they just pump using, maybe you use your mouth or you use any other thing to pump it, and after a time it will burst. What makes it to burst? The air inside it expands. Why is it expanding? Because there is an increase in temperature of the system or of the atmosphere. So the increase in temperature normally leads to an increase or an expansion of gas. So there is going to be volume, increase in volume, increase in temperature, increase in volume when you go to Chancellor. Increase in temperature, increase in volume, then there is going to be decrease in pressure. That is. Okay, somebody said she did not understand the dissolution process. We have NaCl, solid, plus water. When you add sodium chloride to water, you understand, it is this your sodium chloride that is going to be forming ions. There are many things we are going to have in the system. For instance, this Na is going to be Na plus, Cl minus. We are going to be having H plus, OH minus. These are all you'll be having in the system. Because you dissolve salt inside water, everything is going to form ions. But this is the one I need. I need Na plus and Cl minus. I don't want to talk. There is also H plus and OH minus. It is accompanied with them. But we don't want to talk about that one. We want to talk about the ions. For you to understand that, for me to be able to put my aqueous. What do you mean by aqueous? Anytime they write equation, when I put S, it means that system is in solid state. When I put L, it means that whatever thing I'm using, that substance, is in a liquid state. Then when I put aqueous, that means that system has been dissolved in water. Do you understand? It means the substance has been dissolved in water. A very good example at home. When you have a stomach, when we're young, and we're having a stomach pain, we tell our mother, "Mom, my stomach is turning me, it's paining me." What will your mom say? Your mom will tell you, "Go and add salt to water." You pick your salt is solid, your water is liquid, then you add the two together. So when you add the two together, this is the solid salt, this is the liquid. What you will be seeing, you in particular, is a water, but it is not ordinary water. When you taste it, you see it is a salt solution, that there is now salt dissolved in the water. There are many things that are taking place in that system that you cannot explain physically, because the salt has now dissolved in the water to form an ion. So these are the ions now we now have in the system. We have Na plus and Cl minus. Na plus, I put aqueous. Aqueous means it is in solution. It is not just sodium. The sodium ion now, it is in solution. Then that's my cations. Cation, then I have Cl minus. Cl minus mean chloride ion is also in solution. Don't forget, you don't call this thing, this is sodium ion, isn't it? You don't call this one chlorine ion, because when an anion, when you see an anion, or you see a negative, an element carrying a negatively charged, what's it called, charge. When an element is carrying a negative charge, then you add IDE, chloride ion, iodide ion, fluoride ion, not fluorine. But if it is positive like magnesium, you can say magnesium ion, calcium ion, aluminium ion. Are you getting this? But when it is negative, you will say chloride ion. We call this one oxide ion. You call this one fluoride ion. You call this one sulfide ion. Then you call this one iodide ion. You understand? So let's do that. Then let's now talk about the entropy of the system. This one is the ions are in solution, and you know what is going on when ion is in a solution. Okay, I'm coming to that question. So you discover that these are in a solution, and the fact that they are in solution, they collide. If you go back to the collision theory, they collide, and as they collide, the entropy here is higher than here. When you are holding your solid and you are holding your liquid. Listen, let me tell you something. Maybe there is something you don't understand. You take your salt, you take your water, before you add them together, that is your reactant. The moment you add them together, there is going to be a mechanism, a process. And that process, a reaction will be taking place. And when that reaction takes place, you will discover that the reactant will now be converted to form product. Not that it will be going to another place, in that same spot. You will discover, before your water was not tasting salt. Your salt has no water. But finally, you will now discover that the water you added is now tasting salt. That is your product. You understand? And the entropy here is greater than the entropy here, because here they were not moving initially, or little movement. But now there is always a disorder arrangement. That's the reason why the entropy here, entropy change, is equal to positive. Now somebody asked the question. Can I see the question? He said, you said when gas expands, what happens? So you said when gas expands, what happens? Like I told you, when your gas, you increase the temperature, you will discover that it expands. And when the gas expands, then immediately, when the gas expands, what happens to the particles? They move far away from each other, because again, when there is a gain in temperature, there is always a gain in kinetic energy. A very good example is when you are frying something, let's say guguru, popcorn, for instance. Initially, those corn will not be moving. But later on, as you are frying it, what happens to the corn? You will see them jumping up. They gain kinetic energy. When there is an increase in what? Increase in the heat process. Heating process, the heat, the temperature. Then, let's look at when you are boiling water. You are boiling water. Initially, you have not, you have not increased the temperature. The water will settle down, no movement. Actually, there is little movement. But later on, when you continue to boil, then the water is now boiling. What happened? Those particles of the liquid will gain kinetic energy due to movement, to motion. Then they will continue to move. The same thing applicable to gas. Gas also has particles. Immediately you increase the temperature, the particles now gain more kinetic energy. Then they keep moving. And now look at it. When the particles are moving in a closed vessel, you will discover that the particles, can I continue? Yeah? You will discover that the particles will be colliding with each other and even with the wall of the container. So because they now gain kinetic energy and it expands, and they gain kinetic energy, they now move faster. Then what happens to the entropy? It increases. So when gases expand, what happens to the entropy? The entropy also increases. So I think I've answered your question. See, let's continue because we still have a lot to do today. Then number 6 now. Any reaction in which the reactants are solid or liquid and one or more of the products are gases has an increase in entropy. Look at it. Number 6. Any reaction in which the reactants are solids or liquids, in which the reactants are solids or liquid and one or more of the products is or are gases. That system will have an increase in entropy. Let me give you I say any reaction in which the reactants are solid. Let's take it bit by bit. Any reaction in which the reactants are solid or liquid, at the reactant side is now a solid, ordinary solid or liquid, and one or more of the products is or are gases. Now let's look at it. E.g., I'm going to see decomposition reaction. A very good example of decomposition reaction is CaCO3 solid to give CaO solid plus CO2 gas. Now check this. If they give you this kind of question, they now ask you, in this reaction, is entropy change positive or negative? You look at the reactant. What do we have at the reactant? Solid. We already stated it, that in solid, what happened? The particles are closely packed together, there is no movement. Then when you check the product, you see solid and you also see a gas. You capitalize on that gas. If the product has a gas, it means the entropy change of the reaction is going to be positive. The entropy change, of the reaction is positive. Why? The product side has a gas, the reactant side has no gas. Then look at this one. Let's assume I reverse the equation. Now, if I reverse the equation, I will be having CaO solid plus CO2 gas, calcium oxide plus carbon 4 oxide to give us CaCO3 solid, calcium triisocarbonate 4. Then what happened here? The product side is solid. There is a gas, there is a solid there, there is a gas here at the reactant side. Meaning this side is going to have more entropy than this side. The entropy change here is going to be what? Negative. Do you understand? So I can still give you another example. What if you have this one? Let's call this one number 1. Number 1A, number 1B. Let's call this one another example. If you have ammonium chloride is a solid. If it decomposes, when you heat it, it will give you ammonia gas plus hydrogen chloride gas. Now look at this equation. When you have NH4Cl, it's a solid here, You have ammonia gas here, you have ammonia gas here. You don't need to calculate number of mole here. Why? Because the reactant has no number of mole. When I was calculating the number of mole, both the reactant and the product are all gases. Or if you have one gas here, you have another one gas here. You know very well that you need to consider the number of mole. But in this case now, this one is solid and the two products are in gaseous state. Then it means this place, the entropy of this place will be higher than the entropy of this place. So the entropy of the product is higher than the entropy of the reactant. So your entropy change will be what? Will be positive. Since entropy of product is higher than entropy of reactant. What happens if I reverse the equation? If I reverse this equation, then you will discover that I will put this one here, I will put this one here. The entropy of the reactant will now be higher than the entropy of the product. Then the entropy change there is going to be negative. So I've given 6 good examples. So let's take it to 7. Then we are going to see 1 or 2 calculations. We are still in processes with positive entropy. When 2 or more gases are mixed together or constant volume, at constant volume there is an increase in entropy. When you mix 2 gases, when 2 or more gases are mixed together, at constant volume, meaning you are not changing the volume is the same. At constant volume, what happened? The entropy change of this system is going to be positive because you are mixing 2 gases together. If you remember, when you increase the concentration of a substance, what happened to the collision of the particle? Then the collision of the particle will increase. Also, it will also increase. Is it working or temper? Or okay. So the collision of the particle will equally increase. It will equally increase. So that is that. So I am done with processes which involve positive entropy changes. Now, I have achieved my first objective, definition of entropy and entropy change. I have achieved my second objective, examples of entropy system, and I have achieved the processes. I even gave 7 processes with positive entropy change. It is not only positive because I also said negative together, because the reverse of the positive will give you what? The negative. Let me ask you this question. I know you cannot answer me. You can answer at the comment section. If your mom gives you milk and tea at home, and they gave you hot water, then go and take tea. When you add the tea and the hot water together, what happened to the entropy system? The reactant, remember, is the tea, the milk, the water. Now the product is your tea that you are drinking. So the reactants are the Milo or whatever, maybe Bonvita or Milo, your milk and the water. Now your product now is the tea, the liquid tea you are taking. What happened? Is the entropy positive or negative? So put it at the comment section. I believe some of you will be typing that. So let's continue. We want to see the last aspect now. This one will take us back to the formula the other time. So that's the last aspect. Sorry, I'm already taking much of your time. I think we started, what time? We started 8:30. And now I was planning to take just 1 hour 30 minutes before. And now, I don't think I have even used, have I used up to that? Okay, we are going to 10 now. So we have used 1 hour 30 minutes already. So don't worry.
1 hour.
Just 1 hour, okay. So we are going to be seeing calculation. Please, I want you to concentrate on this calculation. It's very simple. Very, very simple. Now, let's see a question. The question says, that's the calculations on entropy. Question we have, what is the entropy change? What is the entropy change for the reaction? What is the entropy change for the reaction? For the reaction, when you have H2 gas plus half O2 gas to give us H2O gas. At this gas, meaning it is vapor. So when you write H2O gas, it means that is vapor. It is not a liquid. But when they put H2O liquid, that shows it's a liquid at 25 degrees C. Did anybody answer my question?
Yes, sir.
What did they say? Is it positive or negative?
Positive.
Oh, God bless you. They said positive. Did
Choma,
anybody say negative?
Choma, Daniela, Esther.
God bless you. Choma, I got your comments. You said positive. Daniela, I got your question. Your answer, you said positive. Which other person there? Let
Esther.
me see. Esther also said positive. I got it. Faith Obuji John says, sir, please come again. I didn't know on which one. So let me know. Then Itunu said positive. Shella said positive. God bless you. So it shows you are all following. So let's continue. We have some value and standard entropy of hydrogen equals 131 joule per mole. Don't forget I told you the units of entropy is joule per mole per Kelvin. Joule per mole per Kelvin. Then the standard entropy of oxygen is 205 joule per mole per Kelvin. Then the standard entropy of H2O, water, that gas, that vapor, is 189 joule per mole per Kelvin. So we are going to see this. We are going to see this. We are going to see this. Now, what is the entropy change for the reaction? And the reaction is H2 gas plus half oxygen gas to give us H2O gas at 25 degrees. Don't forget, your oxygen is having half. It's having half now. Now, solution. The first thing is to write my formula. What is my formula? My formula says entropy change for a reaction is equal to sum of entropy of products minus sum of entropy of reactants. Now, I now want to divert this equation to form on this formula to this equation. And I have my entropy change of system. Because what is my product? We have only one product, which is H2O gas. So I will just say entropy of H2O gas minus, how many reactants do we have? We have 1 and 2. We have 2 reactants. So I'm going to put it inside bracket because it is sum. I will add the 2 together. Entropy, standard entropy of hydrogen gas plus, because it's reactant, I have to add these 2 together. Plus, if you remember, I told you are going to multiply the number of mole. 1/2 times entropy, standard entropy of oxygen gas. Did you see that? So this is this is entropy of products, which this is the product minus, remember it's product minus reactant. Our reactants are 2, while the product is just only 1. So this is product minus reactant. This, when you are writing your reactant, you have to put the 2 together. But remember to multiply your half. Now, what is the value? What is the value of your entropy of H2O gas? Is 189. I will only put the value now under it. 189 minus, open your bracket. That of hydrogen is what? 131 plus let me use square bracket here, plus 1 over 2 times that of oxygen is what? 205. Then I want to close my bracket. You can see a neat calculation. That is how I want your calculation to be on your exam day. A very neat work. I love neat work and a good handwriting. Now, we are going to do some calculation. We have this 189 minus, I cannot do this one. Make sure, remember your board mass, you multiply this one first. You work with the bracket first. This is 131 plus 1 over 2 times 205. It's just like 205 divided by 2. If you write 1 divided by 2 times 205, it's more or less 205 divided by 2. And I think that will give us what? Please, do you have a calculator there? 205 divided by 2. Let me make use of a calculator very fast. So 205 divided by 2. I have 102.5. I have 102.5. Then here my standard entropy change. Can they still see this down?
Yes, sir.
It's got to 189 brackets, or okay, I cannot say minus. Add these together. If you add the two together, you have 233.5. 233.5. Then my final answer now is equal to 189 minus 233.5 will give us minus 44.5. What is my unit? My unit is joule per mole per Kelvin. Joule per mole per Kelvin. That's it. Let me see if at the comment section.
Sir, please, I don't understand. Can you come again?
Somebody want me to come again. Okay. So it is better not for me to. Please, can the person type where exactly you don't understand? Okay, let me explain the question from the beginning. What is the entropy change for the reaction? What is the entropy change for the reaction? If you have this reaction, hydrogen plus oxygen to give us H2O at 25 degrees C. Hydrogen plus oxygen to give us H2O gas at 25 degrees C. Then we have all these values, they are questions. These are questions. They will give you, they supply all the values. Standard entropy of this hydrogen is 131 joule per mole per Kelvin. Standard entropy of oxygen is 205 joule per mole per Kelvin. Standard entropy of H2O gas is 189 joule per mole per Kelvin. Now, we now want to do our formula. Our formula is, remember, normal. The normal formula is entropy change is equal to sum of entropy of product minus sum of entropy of reactant. That is our normal formula. Then from here now, entropy now change. What is my product? My product is H2O gas. I will put entropy of the product, H2O gas, minus what is my reactant? My reactant is not just one, but two. We have two reactants. So some means you must add these two reactants together. This is the first one, standard entropy of hydrogen, the first reactant. Then you will add it plus this number, you must use it to multiply. I did not multiply this one because it's just one. 1 times 10 is still 10. So plus 1 over 2 times the value of this, you write this on standard entropy of oxygen. So that's the formula. Then entropy change now is got to what is it called? The value of H2O. You will now go back to the question. The standard entropy of H2O is 189. You write it there. This is your minus. The standard entropy of hydrogen, what is it? It's 131. You write it there. Then plus, then half times what's the value for the standard entropy of oxygen is 205. Then I put it there. Then I have this equals to 189 minus board mass. work on this first. 1 over 2 times 205 will give us 102.5. Then add it to this 131, you will get 233.5. Then you have a 189. 189 now minus 233.5, you have minus 44.5 joule per mole per Kelvin. Did you see your entropy change here is what? Is negative. It is not positive. And if entropy change is negative, listen, if entropy change is negative, it means it is not spontaneous. But if it is positive, it is spontaneous. When we get to free energy, when free energy is positive, it's not spontaneous. When it is negative, it is spontaneous. But we are not talking about free energy now. When entropy change is positive, it is spontaneous. When it is negative, it is not spontaneous. So this entropy change decreases because it is negative. It decreases, not spontaneous. It decreases. But if it is positive, it is what? It increases. It is spontaneous. I'm going to be giving you another example, which is going to be the last example. The last example for the day. I want to try to stop by 10 o'clock. By 10 o'clock. I'm going to clean this question now. Let me clean the question. Then I'm going to leave this. I don't know whether somebody is writing the question. Ignoring the effect. Ignoring the effects of entropy change. This symbol is entropy change for those of us that had physical class with me. This symbol is entropy change. Ignoring the effects of entropy change on the reaction. On the reaction. Now see the reaction. CaCO3 solid. That's calcium trisulcarbonate 4 to give us our quick line. Calcium oxide plus carbon 4 oxide gas. And considering only entropy, and entropy is S, would the reaction be expected to be spontaneous, Don't forget, before you can say whether the reaction is spontaneous, you must get a positive value. If it is negative value, that means it is non-spontaneous. So let's see, I have not written the value, the given value. The entropy value for calcium carbonate and the rest. So we have this of calcium carbonate will be equal to 92.9 joule per mole per Kelvin. Will be equal to 39.7 joule per mole per Kelvin, and this to be equal to 214 joule per mole per Kelvin. Solution. Good. If you did not get it the other time, I want you to concentrate now. You are going to get it perfectly this time. Please let me check whether the system, the network is fine.
Yes.
Okay, thank you. Now, ignoring the effect of enthalpy change. This system is an endothermic system. Endothermic system is an example of what is it? I mean, this system CaCO3, the composition of calcium carbonate, is an example of endothermic reaction. So, and the value of endothermic reaction is positive plus it. Do you understand? So we don't want to talk about the they say ignoring the effect of enthalpy change. The enthalpy change here is positive if you have to talk about enthalpy. But we are not treating enthalpy, we're only talking about entropy. Now, the question says ignore. Ignore the effect of enthalpy on the reaction, enthalpy change on the reaction. This is the reaction, and considering only entropy. Now we have to consider only entropy. Would the reaction be expected to be spontaneous? Naturally, if you look at the example of spontaneous reaction, I mean, what is it called, of processes with positive entropy, you should know that this reaction is going to be positive. It's going to be positive. Why? Check. This one is a gas. The reactant has only solid. Sorry, the reactant is all solids. While the product is solid and gas, there is gas. Of course, it's going to the entropy change is going to be positive. So, but we have to, to confirm our theory with calculation. We have to back it up. Let's see by calculation. Now, that lady that said, or the guy that said he did not understand, look at me now and get it. The normal formula for entropy change is entropy change of reaction is equal to sum of entropy, sum of standard entropy of products minus sum of standard entropy of reactants. Good. Did you get that? That's just the normal formula. Now, from here now, the entropy change now of a reaction is how many products? Look at it. We have two products. So let's deal with the product first. Only product. Entropy, standard entropy of the first product, CaO, calcium oxide, plus standard entropy of the second product, CO2 gas. Now I'm done with that. Now, remember, I'm done with product now. Let's go to the reactant. Minus entropy of the reactant. Standard entropy of reactant. What's my reactant? CaCO3. CaCO3 solid. Now, did you get it? Now, from here now, we will now include those values. Sometimes they can give you the enthalpy change to calculate any of this. It's very simple. It's very simple. You just apply your mathematical knowledge. So, standard entropy now equals to, we have entropy of CaO, calcium oxide is 39.7 plus that of CO2 is 214. Then minus that of calcium carbonate is 92.9. So from here now, my standard entropy is going to, if you had this and this, it will give you 253.7. 253.7 minus 92.9. Then my answer now is equal to this minus this will give you 160.8. Approximately will be 161 kilojoule per mole. Now you should know the reason why I approximate, because in Nigeria, when you are doing your calculation in chemistry, you have to leave your answer in 3 significant figures. So now we have gotten this. Is this value positive or negative? It's plus already. It's plus. It's not a negative value like the other one we calculated. So it's a positive value. So since our entropy is positive, so what happened to the system? Is it working? since our entropy is positive, then what happened to the system? You will say the entropy change is positive, so this reaction is what? Spontaneous. Since entropy, standard entropy change is positive, therefore the reaction, can you capture this please, is spontaneous. Okay. You have a question?
Yes, sir.
Let me see the question.
No question.
Okay, not a question. Okay, thank you. So that is that about that. I believe you since entropy change is positive, therefore the reaction is spontaneous. Thank you very much. I make use of my time. This is 1 minute to just 1 minute to 10. So I am going to give you an assignment, but my assignment is going to be on your WhatsApp group. So I'm going to snap the note and drop it on the WhatsApp group. If you are not in WhatsApp group, you can eye me with this number. So we are going to add you up to WhatsApp group. So we are going to be stopping now, and our next class is going to be on Wednesday, because tomorrow I will be live here with SS1, where I will be taking them acid. I'll be taking them acid, base, and salt. So if you are interested in joining SS1, you're also free. You are not paying for this. This is free, and free indeed, because free free is salvation. So we are giving this all free. And though we got it with money, we paid when we got this, but by God's grace we are giving it free. And make sure you have enough data, and get yourself prepared. And for anyone that missed this class, you can tell them to go back and rewatch, because it's going to be on the page. So we are going to see next tomorrow by God's grace by 8:30. By is it Thursday?
Yes.
Okay, tomorrow is Wednesday. Sorry, I'm missing this. So tomorrow is Wednesday. I will be with SS1. Then on Thursday, I will be with SS2. So, or the white and jam student. So on Thursday, we'll be talking about free energy. So we are going to be talking about free energy. So get yourself prepared. Then I want you to like this video. You go there, you like this video. If you just log in without following, please click on follow. You have to follow this video. Yes, and you can also invite your friends that are not from your schools. So invite your friends, from anybody that want to write WAEC, anybody, invite. Even if you have a friend abroad. So this topic is going to do them a lot of good. Thank you very much. And you try to see if it's possible for you to download. It's not going to be easy, because we spend a lot of time. It's going to be more than a Nigerian movie. God bless you. Then you cannot do without appreciating my wife, because it is not easy for somebody to abandon her work just to stay behind the screen and make sure everything she has been. The only time she went to receive call, and they took light, I had to run and start doing this. So it is not just easy. Then appreciate my baby as well, because he was not even crying. I was thinking he would be crying, so he was not crying. So thank you very much. So baby Nerry, say thank you. Say thank you with them. Say thank you. All right, bye bye. Please let me off.